So far, we have been very, very limited on what we could do with antiderivatives. We have our basic antiderivative rules, which we can sometimes use in complicated functions if we could rewrite, if we can divide, rewrite to be a power rule. I don't know how many trig identities you've had to use, but we could use trig identities, but that really still limits us to a lot of antiderivatives we still cannot take. Okay? Some of you have been referencing the chain rule. There's really not a chain rule for antiderivatives. We think about what the chain rule is for derivatives, and we've seen that with sine of 5x, right? Or e to the 3x, and we've kind of thought about those. But what happens if we have sine and there's an x squared in there? Or we have functions that are multiplied together, okay? How do we attack antiderivatives in that way? So we're going to work on a strategy called U substitution, and this is what we're going to work on for the next 3 days, okay? We're going to start out with the basics today. We're going to add in some more of our functions tomorrow, and then we're going to look at some more complicated cases on Monday, all right? The biggest thing that we need to be careful with here, I'm teaching you a strategy. That doesn't mean you have to use it at every single time. There's going to be times that we don't need U substitution for. So it's important that we look at first, is this simple? Okay, if it's not simple, can we use U substitution? Okay. So U substitution brings in our derivative chain rule. Okay, and this is kind of how it's formed, all right? We know, and just kind of hang back with me for a little bit. You don't have to write this down quite yet. But we know that the derivative of a composite is f prime of, keep the inside alone, times the derivative of the inside, right? So if we have something inside of our integral that looks like that chain rule, then we need a way to go backwards, okay? I'm going to go ahead and have you write down what's in yellow to bring to your attention that we're working with that derivative chain rule, okay? And to bring your attention to the facts that we're looking for compositions, and that's what really is going to need to stand out to us in our antiderivatives. The reason we're going to have to work on this for a few days is they're not always going to be perfect like they are in that yellow highlighted portion. Not everything is always going to be there that we need, and we're going to have to adjust to that, and I'll show you what I mean here later on. So U substitution is going to work when we have a composition inside of our integral. Well, it works most of the time. And the goal of U substitution, don't write this down, but we're going to go backwards through our chain rule, okay? What's going to happen is we are going to let U equal g of x, or our inside function, and we'll write down some steps here on the next slide. But we call it U substitution because we take this inside function and we replace it with U, and then we change our antiderivative to be in terms of U instead of in terms of x. So we create this simpler antiderivative that we can then take and then go back to, okay, what was u in the beginning? Okay. We can't think of the chain rule in terms of taking antiderivatives. Like, it just doesn't work the same. U substitution is our chain rule for antiderivatives. Okay? So this is how it's going to work. We are going to choose a u. Okay? I'm going to have you look for what's the inside of our function. Okay? If we have a composition, what's the inside? That's typically what we are going to choose for our u. We're using u substitution because we can't do it with any of our normal rules. So if there's a composition, we can pick the inside to be our u. But we need all of our derivatives to fall in place, right? I'm going to go back to this slide real quick. You know, it has to be true that if g is in here, then there's like a g prime out here somewhere. So when we let u equal that function, we're going to have to differentiate like we did back in our differential section so that we can account for that g prime being in our antiderivative. This also helps us with the substitution. So not only are we changing g of x to u, but we can't have a u and a dx, right? Everything has to be a u. So we have to go back and we have to rewrite everything in terms of u, including the dx. So this differential step right here is going to tell you what dx is so that we can replace it in terms of du. Once your integral is in terms of u, then we can actually take the antiderivative using our basic rules that we've learned. But since we started out in probably something in terms of x, I want your answer to be in that original form. So whatever your antiderivative is, we need to go back and take u and change it back to whatever u was in the beginning. If u was x squared, then all of your u's need to be replaced with x squared. Is that too many? Next.
No, it's bad. I like it.
Okay. All right. So, in terms of notes, the rest of our notes are examples and how things kind of fall into place with this method. Okay. So I'm going to first give you an example where things work out really, really nice. Okay. Go ahead and write it down. And let's think about this. If I were to give this to you on Tuesday on your pink sheet, is that when I gave you the pink sheet? Yeah. What would your only strategy be? Oh, yeah, probably cry because you would have to multiply out x squared plus 1 to the 50th power. Okay? Now maybe Pascal's triangle can help you there, but that would be an awfully far way down to go on Pascal's triangle. Okay, it's not efficient whatsoever. Okay? But since we have a composition, and this doesn't always have to be there, but what we have is a composition multiplied to something, much like we saw right here, right? A composition multiplied to something. Okay, this is a good candidate for U substitution. Okay, our composition, a function inside of another. What is in the inside of our function? X squared plus 1 is being raised to the 50th power. All right, so what we can do is we can let U equal that inside function, x squared plus 1. We then need to differentiate using differentials. Okay, so don't write this down right this second because I want to remind you what we did with differentials. So if we're taking the derivative with respect to x, we would write du over dx equals 2x, right? But with our differentials, we separated the dx from the du. So what we would write is we would take this dx and we would take it over to the other side, like that. So du equals 2x dx. Do you remember doing that? No? We did it, I promise. In Unit 3, in fact, like 3B. Okay, regardless of if you remember it or not, does it make sense why I can move the dx over? Because it was like a fraction, I move the dx over. Okay, now what does that allow us to do? Why do I want you to write it like that differential? Well, now we can take x squared plus 1, and we are replacing that with u. So we have u to the 50th power. And look at this. 2x dx equals du. Look at what I have right here. We have 2x dx. So we can replace it with du. And now we have an integral where everything is in terms of u. And it's a simple rule, isn't it? U to the 50th power. We can take that antiderivative. Before we do that, can I clarify anything that we've done so far? Okay. So u to the 50th, our antiderivative would be u to the 51st times the reciprocal of 51 plus c. But would I want you to leave your answer like that? No, we need to take this and we need to change it back to something in terms of x. So since u we set equal to x squared plus 1, then we need to write this as 1 over 51 x squared plus 1, the quantity to the 51st, plus c. What did you say?
No, I was just trying to figure out how we did it. I was wondering why we put the U in there, but then I figured out we did it to remove 2x dx.
Yeah. We basically went from a product to just a single term inside of our antiderivative, which is nice. All right, I'll look at another one. Maybe a little trig action here. Okay, so what I notice is that we have a composition multiplied to a second function. You see that? What is the composition piece? The cosine of x cubed is our composition. All right? So what we need to look at, and stepping back for a moment, if I'm looking at this, we have a product. Do we have a product rule for antiderivatives? No, there's no such thing. Like, we literally just have our basic rules and now use substitution. Okay? So since there is a product, I mean, that's kind of a red flag, like, ooh, we're not going to be able to do anything here. With polynomials, maybe we could multiply out, but we don't even have that choice. Okay? So our composition part is right here. X cubed is inside of cosine. So that would be one place to start. Okay? U, we could let equal inside of cosine x cubed. And if u equals x cubed, then when we take the derivative using differentials, du is 3x squared dx. Are you okay with how we're writing? That worked out nicely for us. Okay. So what's going to happen? Cosine of x cubed becomes the cosine of u. Left over, we have 3x squared dx. And technically, like, we can rearrange because of the commutative property. Here is 3x squared dx. So we can replace 3x squared dx with du. And now we only have to worry about the antiderivative of cosine. Braden, what is the antiderivative of the cosine of u?
Sine x cubed third.
Okay, yeah, you're like a step ahead of me. Let's just say sine of u plus c. Okay. Now, since we have u inside, we can replace u with x cubed. All right, you ready to do one by yourself?
Yeah.
Max has confidence. Okay, I want you to work on this one. I do not mind if you use the assistance of your peers, okay? For sure, I would like you to check your answers with the people that you sit by. I want to make sure you're getting to the same place. But this is one you're going to do without me. Compare your work with the neighbor. Brenly, what'd you use for you?
2x to the 4th.
which means your du was?
Ax cubed dx.
Okay, that worked out nicely, didn't it? Okay. So, you would have had the integral of secant squared of u du, which should have given you tangent u plus c. So as I was walking around, this is what I was seeing. Tangent of 2x to the fourth plus c, right? Okay, and the three problems we've done, what has been really, really nice? Okay, our du has been exactly what's in our integral, right? Okay, that is a very rare case, okay? It's not. Now, let's just kind of take a step back. So our coefficients have been really nice, okay? But what's also something I want you to look at, we had like a 4th degree polynomial inside, and on the outside was a cube, right? Over here, we had a cubic inside, and on the outside was an x squared. Do you see how there's that relationship there with the derivatives? Okay. Well, let's look at this right here. Go ahead and write this down. And something I notice about this problem, okay, first of all, we do have a composition that's multiplied to another function. Inside, I have a cubic, right? Outside, we have an x squared. So that's a good sign, all right? But you'll see here why it's a little different from the ones before, okay? So we have this composition right here multiplied to x squared, okay? This is not something we could do with our basic antiderivatives. Even if we change this to a 1/2 power, we cannot take that x squared through. So we're kind of stuck there. So we could let u equal the inside of our composition, which means that du, yes, I do. Sure. Yeah,
I just want to learn.
Mr. Grell would like to see you.
If it's for the same thing, I just feel like
It could be. Okay, so du would be what? 15 x squared dx. So it's close. Yeah.
What you have to do, I'm guessing, is make it so coefficient happens to go away. Or
Okay, so we have x squared dx in our integral, right? And we have x squared dx right here. So what we're going to have to think about, we have that extra 15 that we're going to have to just divide over. So 1/15 du is the same as x squared dx. Owen?
Yeah.
You okay with that?
Sure.
Okay. Do you have a question? Okay. So when we come over here, we can change this to u to the 1/2. And then x squared dx becomes 1/15 du. So what I'm going to do is I'm going to just throw the 1/15 out in front because he really doesn't matter until the end. And then place my du at the end where it should go. So now everything's been replaced, right? We have the square root of u And then everything outside of the square root got replaced. Any questions before we actually take the antiderivative? So now, we know that our antiderivative is u to the 3/2 times 2/3. That 1/15 just stays out in front multiplied. So we have 2 over 45. Our u, which is 15x cubed plus 4 to the 3/2 plus e. Oh, I don't know why it's 15. It is definitely 5. I was looking at this, but my eye must have caught that one when I was writing. Thank you. Okay. So that didn't have exactly what we needed on the outside, but at least the derivative relationship was there to where we could just adjust with a constant and then we were good to go. Okay. And that's probably more the type of problems than you'll see than the first couple that we did. All right. So let's take a look at this one right here. So first of all, I see that we have a product, which really is not good news. Okay? If we had a product before, we could try to take the multiplication, but since we have a trig function, that's really not enough. Okay? So the multiplication is a roadblock for us, but luckily our product is of a function and a composition. All right? So Allie N, if you were to choose something to be u to try, what would you choose? Okay, so we could try u equaling x to the 6th. Okay, and some of you are looking ahead and seeing, ooh, we have x to the 5th on the outside. That's good news, right? So if du is 6x to the 5th dx, we need to keep in mind that we only have x to the 5th dx in our integral, and we don't want to change the value of our integral. So in order to replace x to the 5th dx, that 6 needs to balance us out on the other side. So 1/6 du is the same as x to the 5th dx. Which means when we come over here to our integral, we would have the sine of u to take care of that. And then x squared, x to the 5th dx is the same as 1/6 du. And I really like to put my constants in front of my integral. You don't have to do that. I just really don't want to worry about them until the end. So then our antiderivative would be negative cosine of u plus c, keeping that 1/6 out in front. So our last step then would be to replace u. So we have negative 1/6 times the cosine of x to the 6th plus c. Is there a way for you to check to make sure your answer is correct? Yeah, if we take the derivative of what I boxed there in green, we should get back to what was inside our integral to begin with. Okay, there is a way for you to check to make sure you did it right. Now, if I were to give you something like this, what strategy would you use on this integral? Okay, I'm hearing two different things. I'm hearing multiply it out, okay, to a trinomial, right? If we tried to do u substitution here, we would get a du to be 6x squared dx. Do we have something squared dx multiplied out in front? We don't. So u substitution is not an option here. Yes, it's a composition, but we don't have what we need out in front. Okay? So our only option would be to multiply that out and take the antiderivative. Okay? Even if we had something like this, what if I changed it to just, whatever. Here we have a composition times a function, okay? More of what we were looking at before, but the relationship isn't there, is it? I need my du to be x squared dx, and I have an x on the outside. So here again, this one, you would have to multiply all of that out in order to take the antiderivative, okay? U substitution opens lots of doors, but it has to, the stars kind of have to align in order for us to be able to use it. All right, Brayden, we have 10 minutes left in class, so I'll let you start your homework since we sped through our warm-up just for you. Oh, you know what? I wrote this as cubed. And that's why, yeah. So this, before you were right. I'm sorry. I meant to write that as a cube, and I did over here. So I was referring to this. But yeah, with my mistake, it would have been fine. Now that I've fixed it, this would not be able to work. Thank you for pointing that out. Max, I swear I changed it.
It's alright. I got a nice block.